Okay, so let's finish with this problem. What is the angle for that you should throw an object? Well, throw an object is maybe not exactly the right way to put it, but to shoot a cannon from the ground that would go the farthest with the same initial speed. By initial speed, we mean the actual speed rather than the two horizontal and vertical velocities. So that certainly is needs an explanation, and that is right here what we talked about. Doing it again. Right here. Okay, so the velocity, where is my velocity? Here's my velocity. This is my velocity. So if we have two functions f and g that represent the location, x and y, with respect to that variable, with respect to t, the variable, the derivatives form what we think of as the velocity. So the pair of locations, two numbers, for each t will also produce the two numbers that form the velocity. Okay, so whatever exactly how it works out, how to visualize it, might be a difficult question. So best we can say is what you see on the left. So we produce tangent lines. If you want to also take into account the magnitude of the velocity, then it gets slightly more complicated. But let's just think algebraically. So then f prime is the rate of change in the horizontal direction, the velocity in the horizontal direction, and g prime is in the vertical direction. Okay, vertical and horizontal could be, it's all relative, so it happens to be paper, you see, or the screen happens to be vertically, so there's one horizontal and one vertical direction, but you can do it on the floor and it will be just as good. So that is my velocity, and then what is the speed? The speed is, well, you can see it, well, this is the speed. The length of the diagonal. Okay? So we have separate velocity in the horizontal direction, vertical direction. Okay? So if we combine them together into two numbers, f prime, g prime, that gives me the direction and the magnitude of our velocity. So, but that's two numbers. But if you think about that, they're two separate numbers, and when you're throwing a ball or shooting a cannon, you're not in control of these two numbers kind of independently. That's just simply not the case. What you are in control of is how fast you throw and in what direction. So that's the magnitude and the direction of motion taken together, but they are literally taken together. The magnitude and the direction of the throw are magnitude of your velocity, also known as the speed, are taken together. But that's not what we want to deal with when we are dealing with a numerical or algebraic analysis. We have to separate x and y. So also kind of two numbers, but totally different numbers. So either it is what you see on this picture, f prime, g prime, two numbers for x and for y, but what the reality is, what we care about is this, the speed, the length of that line, and this angle. Okay, so let's call speed s, and direction or angle alpha. So this is what you have control over. Well, we assume that the speed is given, so you have amount of gunpowder fixed, and so say where you're shooting the same bullet, for example. Okay, so that is fixed. Then the only thing that is in your control, under your control, is the angle alpha. Okay, so then we have to translate between these two. Unfortunately, we do need f prime, g prime in order to find f and g, and that is why we don't really have a choice in the matter. We have to connect the two, and fortunately it is nothing but simple trigonometry. Okay, so G prime is equal to S. Well, let's start with F. So F prime on the x-axis, F prime on the x-axis, F prime is S times cosine alpha, and G prime is S sine alpha. Okay, so that's the relation between these two different ways to represent things. The reality, where you only have access to the speed and the angle of the throw, and then the two derivatives, two velocities separate with respect to x and y. Okay, so that's why we carry out this plan. We carry out this plan the way I did. I started doing it here. So as you can see, I have S here, my number. So I assume that my speed is 100 feet per second. Any number is fine. And then alpha is the angle I put at 0.5, which is measured in radians. But we'll figure it out later what is the reasonable number is through trial and error. So then, as you can see, everything else is the same as before. So if you look at x double prime x prime x, there is no horizontal acceleration. The initial velocity, look at the picture, at the formula over there. It is, as you can see, it is literally S cosine alpha, right? You see it right at the top. The blue one is 100, that's S, and underneath is a red one, and that's alpha. So the formula is S cosine alpha. Okay. Okay. So and then we start the next number to our right. Next one is our initial location, and it is 0. So we will be shooting from right here. See this point over here from 0, 0 point. Okay. So now looking at the same for the vertical three numbers. Vertical acceleration is -32. Vertical velocity, initial velocity, what is it? Once again, we'll look at the formula, and you can see here it is once again S sine alpha. Okay, so as you can see, we distribute that S into the horizontal and vertical components. Not distribute, but rather decompose. We decompose into horizontal and vertical components, and then once we have, then everything x and y do not interact with each other, and we have horizontal and vertical developments are separate. So those are two graphs on the right, the one. So as you can see, the one at the bottom is, in fact, it is x because there is no horizontal acceleration, and then as you can see, we're progressing in a linear fashion in the horizontal direction. In the vertical direction, we have acceleration pointed downwards. That's why we have a parabola. And then if this one is x and y combined together, as you can see, x and y combined together, and we see that point over here or here somewhere, I don't know, you can see it here, where it crosses the x-axis, that's how far it goes. Okay, so you can certainly see it in the data. It doesn't have to be plotted in order to be understood. I could just simply pull this away and ask myself, at what point do I hit the ground? What does it mean for the ball to hit the ground? It means that the vertical location is 0. So I look at y. So I'm looking at this column. These are the y's, and I scroll down until I reach 0. Okay, so we did that before, I think. So this is where this is where things are happening. As you can see, y between it was 2.15 and then -0.017. That is where somewhere in between 2.9 seconds and 2.95 seconds we hit the ground. Okay, so that's where it has happened. I certainly can. Well, that may be not the best way to do it. I could certainly improve the accuracy probably because I have extra room anyway. So how about I put here 2? Wait. Okay, so the picture is a picture of the data you can look at, and you can see that it goes about goes as far as 250 feet plus maybe 260 feet, right? You can see it on the graph. Okay, so now what do we do to answer the question? Well, yeah, we already know the answer. So so it goes. Well, let's do it anyway. Where is it? So we were going to y prime pretty far, and we just have the same information, only more accurate. So as you can see, it takes about 2.94 seconds to hit the ground. It goes over. These are the numbers that we care about. That's how far it goes, about 260 feet. And well, that's pretty much it. We can also see how hard it hits the ground. These are the x prime, y prime are here. Also, we can figure that out. But at this point, we're trying to solve the problem: how far, what is the best angle? So this angle was picked, 0.5 radians, whatever that is. So what do we do next? Increase or decrease, right? So at this point, we don't know which is it better or not. So let's increase it by significant amount, and so we'll see if it improves. Hopefully. So how about one? Well, one maybe. How about 0.7? Okay, 0.7. So 260. Remember, 260 was the distance. Now, oh, I don't have enough. Okay. Okay, so it's better, right? You can see we are going almost 300 feet. Okay, so it has improved. Let's try to improve some more. Maybe we proceed in the same direction. 0.8. A little bit better. 0.9. 0.9. Not as good, right? So the previous one was higher than 300 feet, and now it is 300 feet. So between 0.8 and 0.8, let me do it one more time. If I go 0.8, it was, as you can see, 320 or so, 310 feet in the distance. So okay, so let's try 0.85. It almost, well, changed a little. So anyway, this is, you can do it more and more accurately if you, instead of looking at the picture, which is the quickest way to do it, you actually scroll down all the way and see how far it went, and then pretty much doing trial and error, you can figure it out. So it turns out that the angle is 0.85 radians. Okay, so it just remains to confirm that 0.85 radians is indeed pi over 4. Well, let me write it down here. If I put pi over 4 over here, equal to pi over 4. Okay, well, 0.79 appears to be closer to the truth. Well, let's confirm that. With trial and error, we got to 0.85, but it seems that 0.79 should be better. Okay, so this one 310 or 305 or so, and this one slightly farther, so it's slightly better. So the theory gives us 79% pi over 4. Okay, so which is not pi over 4, meaning 45 degrees. Okay, it is just, I want you to see that the result is not predictable. It's not. It is a pure coincidence that we are shooting exactly in the middle, exactly in the diagonal direction, not in just any angle between 0 and 90 degrees, but exactly halfway through. Because there is no symmetry here in the situation between the horizontal and vertical. All we know, if we shoot horizontally, we get 0. If we shoot vertically, we get 0, which means that we got to get somewhere in between, which is probably there is the best way to do it. But that it is 45 degrees, it's coincidental. At least I don't know an argument that you can make without actual computations, either trial and error or calculus, to provide evidence that it is indeed 45 degrees shot is the best one. Okay, so well, if you know, let me know if you know of such an argument. But it appears that because of the asymmetry, you really have to solve the problem either numerically, as I did, or analytically. What does it mean analytically? It means that, well, how would you solve the problem analytically? So how do you prove that it is exactly 45 degrees, not approximately 45 degrees, which is what we demonstrated at best? How would you try to prove that it is exactly 45 degrees? So the problem is an optimization problem. Okay, optimization meaning that there is a parameter alpha, and there is a certain function to be maximized. So in other words, it's calculus 1 problem, except the challenge is to find that function. But it's really not, with all this what we've got, it is not hard to find the formula for when the initial velocity is given, and to find where it's going to land. The distance is not that hard. I mean, it is. We did it almost exactly that some time ago. If I wonder if we can, something that we started with. Yeah, something like this. I'm doing it again. Yeah. So motion, and we remember integration, so we pretty much find that formula through integration. So because the accelerations are given, the initial velocities are given, and by integrating twice, we can find our location. So that's what we did early when we started with the topic of Permitir curves. That's exactly what we did, and that's the formula over there. See, location of y. That is the for that particular setup. Is the altitude as a function of time. So to find out how far it went, how do you do this? Is set y equal to 0 and solve for t. Okay, so that we pretty much did something similar. So anyway, it can be done, and it is really just an exercise, I suppose, into manipulating these formulas and a little bit of integration and a little bit of algebra. Okay. Okay, so here it is. So the problem is solved, but I still want you to appreciate our ability with what computers give us. You don't really have to do the hard stuff of calculus, integration, or anything like that. When you just do numerical experimentation will give you the answer very quickly if you just understand what's going on. Okay, so from this point we proceed towards well, a little bit more of multidimensional calculus, and that is going in the direction that is opposite of what we just been doing, and that is a Permitir curve is a function, remember, with input is t, time, or whatever it is, could be anything, and a number, and then output a point on the plane. So once again, it is the best way to have an example of a Permitir curve, and that is incorporates everything that you might face when you study them. Is motion. Okay, so motion, t is time, x, y is location, and that's your Permitir curve. So later on, when you get used to these things, you should start thinking about this in the abstract. But the beginning is the motion on the plane like this. Okay, so remember it's like a trip, a plan of a hike through on the map. Okay, so you have a map, maybe like this. And on that map, you draw a picture and indicate where you're going to be. You draw a line, and then you indicate where initial point, and then every time where you're going to be reaching what point at what time. Okay, that's the best way to think about Permitir curves early on. So now you can flip it, and then flip it. As you can see, input is number, and output is a point. Now what is it's the opposite. So input is a point on the plane, and output is, say, z, a number. Okay, so point on the plane as opposed to that's not it. I mean, this is a number. So it goes in the opposite direction. It's the input becomes output and vice versa. Okay, so there is a very good metaphor for this thing again. Let's keep doing it. And that is a second part of your plan. As you're planning your trip, what you might be also interested in is the elevation. So, well, first of all, what I want to point this out, that we're talking about a function of two variables now. So the location is, in fact, a point on the plane is xy, is a location on the plane just as it is here, but this time it's not the output, it is the input. And then the output could be elevation. Okay, so in other words, if you took a piece of paper and you plan your trip or your hike, but it is like a bird's eye view, and then there is something that is not here on this chart, but might be elsewhere, and that is so it's the same chart, but you might have elevation. So, have you seen something like this? Maps like this. So, what do those curves stand for?
Usually, like how high or how deep something is.
Yeah. So they're accompanied by numbers. So, for example, you can have 100, maybe this one is 200. So elevation of along each of these curves, the elevation remains the same. So you just assign one number to each of these curves, and it gives you the path along which, if you go along that path, you will not be climbing, right? So that's what it is. So 200, 300, 400, like this. Okay, so that is something that is would be very nice for you to bring with your, as you plan your trip, because the first one will only give you the how far you go in the horizontal on the plane, how far you go in the horizontal direction. How hard it might be to climb is not present on that picture. So, but if you bring into this story this second piece of information, rather than only that, what the first map might indicate things such as miles, horizontal. It might indicate maybe roads, maybe cities, maybe rivers. So it's all important, and that for your trip, and maybe like trails. But then if you actually go, it's not desert, so maybe it is there are mountains. Then you have to plan how hard it would be to climb every time, and then you have to combine these two together. And as you can see, you have two things right away, two things that you study in calculus. Once you go beyond calculus 1 and you start studying functions of several variables, and that is a function of a Permitir curve. To begin with, input is a number, output two numbers or a point. And then number 2, a function of two variables. There is no fancy name for it, unlike Permitir curve. So just say usually that's the way it is described, function of two variables. What are those two variables? They are simply two coordinates of that point on the map. And then you attach elevation to this you attach a number z, which is the vertical location of the terrain, right? So for each location on the map, same map that I have in blue, then you have elevation. Okay, so roughly what the picture would I have here if I try to actually, I mean, why it is done this way, it is not the terrain that you see, it is because it has to be on a piece of paper. That's why we resort to this idea of frequently drawing those curves. Okay, so but in general you can think about it as if there is actually elevation indicated by those curves. So it looks like a mountain, right? So I don't know, like this, a mountain. Okay, so and then you could actually combine these two together, and if your plan has been set, your plan, that trip, the top you combine with the elevation map, and what do you get if you combine these two together? So this one from t to xy, that's the first function Permitir curve, they plotted on the left, and then for xy to z. So these are the two functions. From Permitir curve, for each time it gives me location, okay, and the second one for each location gives me the altitude or the elevation. What do we call this? Well, it doesn't matter what it's called, but if you can tell me what the result of this is. If I combine these two functions together, what's the result? Well, look at the beginning and the end. So if I combine them together, then xy becomes simply an intermediate information, so which is thrown out. So for each t, I will get z. So how do you describe it? There, that's right. Elevation is a function of time. That's what you're going to get. So that is exactly what you might be interested in terms of figuring out how hard it would be to take that trip. So you have planned a trip, and now you know, can I take it? And that function, that if a combination of these two will give you a function that I put in orange over there, will tell you how hard it's going to be, because you will know how high you will be every moment of time. Suppose the horizontal direction is easy, but the climbing is steep, and that's what you're worried about. And that's what you have. You call well. Do you remember what it's called when you combine two functions consecutively? It's called decomposition. And you can compose functions, not necessarily a function of one variable. So you remember composition, you see then whenever you do the chain rule or anything like that. So that is a similar situation, except now you have way more variables, more dimensions to worry about, and but the calculus still applies. We're not going to do a lot of calculus. We'll just touch upon a couple of things. I want to do, however, numerical. I want to demonstrate once again what you can do with the numerical visualization. So we know how to visualize functions, a Permitir curve like this. So two functions of the same variable. That's what combined together gives me a Permitir curve. This one. Okay, so this one. Now what I want to do is I'll start over, and I want to visualize, using Excel once again, a function of two variables. Okay, which will produce a terrain of some kind. Okay, so let's start from scratch. So I will still have my h, sort of. That it will be the progress of my xy along xy, x and y, so say 0.1. Okay, so I will, So if we look at this picture again, as you can see, we're looking at the bottom picture. Okay, so the x is horizontal, y is vertical. Okay, so to begin with, before we get to the function, we have to produce all the possible inputs of this function. In other words, pairs of x and y. For each x, there will be a string of values of x horizontally, and then there will be a string of y's vertically. So let me try to put it here. Maybe, yeah. No, wait a minute. This is a little bit, kill this, a little bit too wide. Okay, that's better. Okay, so let me put it here. Okay, so I'll go x horizontally, well, x horizontally and y vertically. Okay, so I'll start with 0, okay, and then I will progress to 1 point at a time, 0.1 at a time to the right. Okay, so it will be then equal to this value plus R2C1, R2C1, okay, that H over there. Okay, 0.1, and I can have as many of these as I like. What did not work out? Why did not work out? Okay, one more time. These are values of x. Once again, a function of the variables. This is one of the variables. Okay. Then I could certainly create values of y and also have a string of y's. But once again, the domain of my function. Look at this picture. The domain of my function is a rectangle over there. Every pair of x and y has to be present there, so that's why I will put x's along the x-axis and y along the y-axis. Okay, so I go the same way. I put 0 there, and once again start adding 0.1 at a time. So I'll have the previous plus, once again, R2C1. R2C1, my value of h. Okay, and I have a few here. Okay, so then for example, this location over here, it refers, as what I highlighted, it refers to, look at it, on the x-axis it will be 0.6, on the y-axis it's 0.4. Okay, so then over here I will enter the value of the function when x is equal to 0.6 and y is equal to 0.4. Okay, so how I will simply, first of all I need a formula. Let's make it up. So how about sine of x, sine x. Okay, so I'll put here R3C. Okay, I'm referring to the entry of x, plus, how about y squared? Okay, so it will be then RC3. Okay, squared. Okay, so you see the formula, right? So sine, the blue one is x, and the red one is y. So sine r squared, x squared plus x plus y squared. Okay. Oh, it certainly is y. And now I can actually fill this whole thing with these formulas. Okay, so right and down. Okay. So the function has been computed this many times. I don't know, 200 times. And we have 200 values of this function. Okay, so you can just look at the numbers. Look at the numbers. You can see how, what I don't like here is maybe one more decimals here. Okay, well, it's not really that easy to see, but so let's not do this. So you can see how the values increase, then decrease, and then you can see these ones. That's where these are the highest points. So it's like a ridge. That's a ridge in the middle that you can see, and you can see negative ones over there. That is the what is it called? Like a valley or a passage, right? So the numbers tells you a lot already, but you can do better than that. Maybe you know what we can do with it. It is called in Excel. It is called, if I can just find it. In Excel, it's called conditional formatting, which is simply coloring. we can color the cells according to the value. And then it will indicate the elevation. You may have seen those maps as well. Well, they're even more typical nowadays when you can use a color in print rather than using those curves. You can simply color it depending on the elevation. Okay, so very easy to do. I just, like I said, conditional formatting and color slides. I will pick 2 colors. How about this one? Okay, it's not very pronounced, but you can tell that the darkest one is there anything more pronounced? Well, maybe, yeah, that's a little bit better. Okay, so as you can see, the low elevation is green over there in the corner. That ridge is visible very light, and I could well, so that's one way to visualize the function of variables by color. The values, how they vary in 2 directions independently, and then there is still, where is the, you can ask, where is the terrain? If this is a terrain, then I mean, this is so 2-dimensional, and terrain is 3-dimensional, so we can certainly try to use the modern computing to actually see the terrain, the surface. And once again, there are options. Charts. So charts, where is my, that's not it. No. Here it is. I didn't select it. Okay, I can try over. Okay, so this is my, select the data, and then I click insert data with a surface. Okay, you see the surface, right? So it is in fact is made like a wireframe because there is no actual surface. What Excel is dealing with is entirely this data, all these numbers, and it is just combine them together into little connect them by edges, and that's what creates this wireframe effect. Even though this is the what did I do? Okay, even though, as you can see, they could actually produce an actual surface. So let's do it. This is an actual surface, and there is a way to look at it from different directions like this. Okay, so that's the surface we have built. You can see those lines. What are those lines? Between yellow and gray. What does it indicate? Levels, not necessarily sea level, but any levels. So those level curves that we drew in the beginning, remember that these are now visible on the surface. So these lines, they are now sort of lifted and now plotted on the surface itself. So they color it in order to create more 3-dimensional effect. But otherwise, this is the surface, and you can certainly vary. I can try to make it something more dramatic, like this. Now, can you see what's going on here? This one has more ridges, as you can see. So what remains is just to so far no calculus really. So what do we care about? What do we care about these surfaces so that the calculus would be applicable? And the same thing. It is the rate of change. Rate of change. How steep is the terrain, for example, in a particular direction. So it's not a choice when you have a function of one variable. It's a curve, so there is pretty much one direction, or the opposite. It's the same thing. But here you could walk in, and then you start with the same location, say maybe here, okay, and then you can walk in different directions. Okay, you can walk to begin with. Well, let me pick this location over here. I could, if I walk along this line, what's happening to the elevation? If I'm walking this way, how fast am I climbing if I'm walking along this line? Can you see the line? Right, exactly, there won't be any climbing. So that direction will give you 0 climbing, 0 rate of change, and 0 derivative, in other words. On the other hand, I could actually start literally climbing like this. If I'm going up that way, it is pretty steep. And then probably you can guess what is the steepest direction is. Well, look at it. Now I'm sort of looking along the same level line that we see if I'm standing over here. If I'm standing here and I proceed in that direction away from us, then you're not climbing. But I could climb if I go in the direction perpendicular to that line. So you probably can see it in in a road or a trail in the mountains. It is in fact they try to make the trail or the road as flat as possible, so they go along those lines. In the meantime, if you actually want to climb, which way are you going to go? You go straight 90 degrees off the road, and that will probably give you the fastest climb. If you go in the opposite direction, 90 degrees, steepest decline. Okay, so that's how calculus applies, and things are not really that complicated if you're prepared to sort of stretch your mind a little bit and realize that function of two variables is a function of, it's like many functions of one variable. In fact, you probably can try to, let me see if I can, oh here, maybe like this. No. There is usually let me try to change the chart. There are the charts, bars, columns. Okay, let's try it. Well, okay, that's not working out. Hold on a second. Where's the 3D? What happened to 3D? Okay. So, I change chart type. There are different types. Columns. That's columns. Pie, bar. No. Not line. Whoa, look at that. Let me try this one again. Why there is no rotation? It's strange. No, that's all wrong. Well, strangely, once again, this is Excel, different everywhere. So what I'm trying to do is, it must be one of these. These. Okay, you see it? So instead of having a surface, I have that surface or that terrain is made of these columns. Okay. So what is the point? It doesn't look as smooth as before, but there is a point here. Let me rotate it slow. Where's the rotation? 3D rotation. Okay. Okay. You can see that you can see a bunch of functions. You can see a bunch of functions of one variable. So each slice is a function of one variable. Okay, and then you can study it with the tools of Calculus 1. So if you these are aligned with the x's, obviously. So at least in the direction of x, and then, you can study the rate of change of the terrain in the, say, east-west direction. You know how steep the terrain is by looking at the derivative of the function. Okay. Similarly, you can do it with respect to y. If I just can rotate it more. It's not as visible. So you can see these, right? They're going towards you, and you can see a bunch of functions. And but there must be a way to align it differently. And once again, can you see the curves moving away from you? Unfortunately, they're not colored in the same way, so it's harder to illustrate that idea. But at least in one direction, you can see how you have a bunch of functions. In fact, infinitely many functions that are a function of one variable. Okay, and then you study them with the just calculus 1. So you differentiate, and you have the rate of change. Okay, so those are called partial derivatives. As an example, the function that I have introduced, and let's see if you can do with this. So f of xy is the function I had sine x plus y squared. Okay, then if we're interested in the rate of change with respect to x, what do? We fix y. In other words, even though x and y are both variables, but we study them one at a time. And how do we take y out of the consideration? We concentrate on one of these curves. So this is the change of x is along this way, and then there is no change of y. Okay, so and then differentiation is entirely with respect to y. So what do we get? This is the notation. So df dx. We do differentiation with respect to x, not to be confused with the differentiation not to be confused with implicit differentiation. So can you differentiate this with respect to x? So once again, y is not a variable. Y does not depend on x. And it is, you can think of it as a constant number. Well, first of all, sine, what are we looking at? It is a composition. We differentiate composition how? Composition of sine and x plus y squared. So how do we differentiate compositions? Well, two functions, right, sine and x plus y squared, combined together, computed consecutively. Okay, so first you compute x plus y squared, and then you apply sine, so it's like, that's the consecutive idea. From x squared computed, then you move on, plug in the output of sine, so it is a combination of two functions, and then the derivative can be found in terms of the derivative of the two functions. So, what's the answer? Nobody remembers the chain rule? Okay, we'll finish this next time then.